Okay, in this video I'd like to introduce a couple of concepts that are very important for, especially if you're doing concepts like quantum physics or something along those lines anyway. Alright, and they are the density of states, the occupancy, the number density and the number. So the first thing I'd like to ask you is, what does density mean? Well, density is the amount of something per unit volume. Okay, so usually it has units. We'll say whatever your something is, that unit, and meters to the minus 3. Okay, that's if you're talking in SI. So the next question I'd like to ask you is, what does mass density mean? Well, mass density, and we usually give it the symbol rho, is equal to the amount of mass per unit volume, and it's got units of kilograms, meters to the minus 3. So you might say, well, let's distinguish it, make it distinct from other forms of density, and we might say it's rho sub m. So I suggest you, how about instead of saying rho sub m, we say it's rho of m, rho function of m. In other words, the variable within which it depends, or upon which it depends, is mass. So you might say that rho of m is equal to m over v. So that is the mass density, the amount of mass per unit volume. Next, let's just to get a feel of this, and I'm not going to be very rigorous here, but let's just to get a feel of it. Let's consider the Bohr model of the atom. So the Bohr model had a spherical nucleus, of dense spherical nucleus, and that was surrounded by these orbits upon which the electrons were on. Alright, and these orbits had a varying energy, with increasing energy as you went radially away from the origin. So for example, this state here, this shell, or this orbit closest to the nucleus had the lowest amount of energy, the next one has the next lowest energy, the next lowest energy, and so on. And when you label them, n is equal to, it's either n or 1, or 0 or 1. So say n is equal to 1, n is equal to 2, n is equal to 3, and so on up to n is equal to n. The difference, of course, between each of these is energy. So instead of talking about spheres or orbits, let's just consider them as being a line. Okay, so this is the same thing as this, except considering them as a line. So say n is equal to 1, n equals 2, that's a 2, n is equal to 3, and so on. Consider these the exact same as these orbits. So on an orbit, an electron can exist. So you could have an electron here, you could have an electron here, and here. So what if you didn't have an electron there? You'd still have a state, or a place where an electron could exist. So you would call it a state. So each orbital or each shell is a state for an electron. So if you plotted all the different energy levels, you'd be plotting all the possible states where electrons could exist. Okay, so these are the states. So that's what a state is anyway. So a state is it's like it's an allowed energy, or a possible energy of a particle, and it doesn't need to be occupied. It's just there. It's like, for example, if you thought about a football stadium. Each of the seats there is a possible state for a person, and between seats there are no states. So you can't sit between the seats, so that isn't a state. That would be something similar to a person being in here. There aren't any states between these levels, so they don't exist. The states are separated by they're quantized, shall we say. So they're not continuous. So it's not a continuum, it's quantized. Okay, there are gaps between them. So like I said, it's quite similar, I suppose, to a football stadium. And if you had all of your states occupied, you would have a full occupancy, shall we say, and you would have no available states. That's what that means. So how about then we say, what does the density of states mean? Well, a moment ago I said that density is the amount of something per unit volume, and we gave the symbol for density as rho. So if we're talking about the density of states, well, it's the number of states per unit volume. So I'm going to say, I don't know what, is it G sub s? I can't remember. I'm just going to say number of states. How about that? It's probably just the number of states and volume. Okay? But because the states depend upon energy, I'm going to give it the symbol rho of E. So that is the density of states, the amount of states per unit volume. So how would you find out the density of states in a football stadium? Well, what you do is you would get a unit area, which would be maybe a meter squared. Well, because we're talking about, in a football stadium, we'd be probably talking about 2D. Yeah, you could be talking about 2D, or we'll say volume. You'd find out how many seats exist in 1 meter cubed, and that would be your density of states. So you might have, we'll say, 400 per unit volume. So that would be your density of states, 400. All right, and that would be the density of seats, or the density of states in your football stadium. So then we need to ask ourselves, what does the occupancy mean? Well, that should be a pretty straightforward concept. It's the amount of states occupied. Going back into your football stadium analogy, it is the amount of seats occupied. So, if you consider, we're talking about fractions. If you say we have 100% occupancy, we have an occupancy of 1. If we have 50% occupancy, we have an occupancy of 0.5, and so on. Alright? So that is what your occupancy is. So obviously, if you want to find out the number of seats still available, or some number unoccupied, it would be 1 minus your occupancy. Alright, that would be the number remaining, or unfilled states. Alright, so yeah, occupancy. Now, in terms of quantum particles, there are 3 types of occupancy. Well, let me think now. No, there are 2 types of occupancy. You can talk about the occupancy of fermions, and you can talk about the occupancy of bosons. Now, I'm not going to go into the details. You could probably look at my video on the standard model, and that might help you with that. The standard model, or wave-particle duality, I suppose they'd help. So basically, particles can either obey fermi-dirac statistics, or they can obey bose-einstein statistics. So fermi-dirac statistics are for fermions, and they, I suppose, would be mass particles, and bose-einstein statistics for massless particles. That's a very general statement, so I'm not trying to be to be rigorous. So we give the variable f of e as the occupancy. Notice it is a function of energy. So the occupancy for fermi-dirac statistics is 1 over e to the e minus mu over kt plus 1, where mu is the chemical potential, E is the energy. And you could, I'm going to say fermi-dirac, and just for I suppose rigor, I'm going to say the bose-einstein occupancy. That's equal to 1 over e to the e minus mu over kt minus 1. So that's the occupancy function. So let's go back to our stadium analogy. What is the occupancy? Okay, so I said a moment ago, if every seat is filled, then you have an occupancy of 1. If every seat is half filled, you'd say you have an occupancy of 0.5. But how would you find out a mathematical function for your occupancy? How would you do that? Now, I'm not going to suggest how you might do that for a stadium, but I'm going to suggest a way you'd know for electrons. Electrons obey fermi-dirac statistics, so if you want to know what the probability of a state being occupied is, you'd say it's f of e is equal to 1 over e to the e minus mu over kt plus 1. So this gives you the probability of one of your states being occupied, or let's say it's the probability of a seat being occupied. So we know that f of e is the occupancy, or the probability of something being occupied, and we could also say that, and we know that the density of states is the number of states per unit volume. Alright, so then how do you find out what the number density is? What does number density is? What does that mean? Well, think about this. What does number mean? Well, number is the amount of something. Okay, so we usually give capital N as the number of particles. We'll say, yeah, particles. So you might say, what is the number of particles in a stadium? If the stadium was full, it would be the capacity. And let's say, I don't know, 30,000. So you'd say capital N is equal to 30,000. That is the number of particles in your system. So we'll say that's N here. That's the number of particles. But what if we wanted to think about the number of particles per unit volume? Well, what is the number of particles per unit volume? You would say it's the number density. The number density. Alright? The next question you need to ask yourself is, how do I find out a formula for the number density? Well, first of all, you need to know what is what is the density of states? Where can people exist if you're talking about a football stadium? Where can they exist? And then you're saying, of all the places that they can exist, how many are occupied? So if I say, I'm going to tell you that n of E is the number density. Okay, the number density, notice of course it's a function of energy. And if I suggest to you that the number density is equal to the density of states times the occupancy. Does that make sense? And it should. So the density of states is the amount of states per unit volume. The occupancy is the probability of those being occupied. So if you look at the amount of states that you have available times the number that are occupied, or the probability of them being occupied, should give you the number of particles per unit volume, n of E. Alright? Next, how do I get the total number of particles? If I know the number density, how would I get the total number of particles? So I say n is equal to the total number of particles. Think about it. If you know the number density, or you know the density of anything, how about this? I ask another question. If you were told you wanted to get the mass of something, and all you knew was the density, and you knew the mass. Well, you knew the density, and you wanted to get the mass. How would you get the mass? Well, you know that mass is equal to density times volume. So you'd find out how much stuff you have, and you'd multiply it by your density, and you'd get how much space you have, multiply it by the amount per unit space, and then you get your mass. So if we have our number density, if we integrate that, we should be able to get our number. So if we integrate the number density n of E times dE between, let's say, I don't know, negative infinity to positive infinity, usually that'd be out of the limits, you'll get the number. Because we're talking about energy, so we're integrating it n of E dE. Another way of writing that is that the number is the integral from negative to positive infinity of rho of E times f of E dE. Alright, because we know that the number density, the amount of particles per unit volume, is equal to the number of states per unit volume multiplied by the probability of the state being occupied, or the occupancy. Another thing I'd like to tell you then, let me think, oh yes, how do you find out the total energy? Well, think about it. If you know the amount of particles per unit volume, and you know the energy per particle, then you can find out the total energy. So, if you multiply the number of particles you have per unit volume by the energy, then you have the amount of energy per unit volume. That is the amount of energy per unit volume. Energy per meter cubed. So how do you find out the total energy? You do it in the exact same way as you found out the total number of particles. So you'll say E is equal to the integral from from negative infinity to positive infinity of n of E times E dE. Or you could say it's equal to the integral from negative to positive infinity of rho of E times f of E times E dE. Very straightforward. If you understand the concepts, it's very straightforward. So I'll just quickly show you a typical kind of calculation. I'm not going to do the full calculation, and neither am I going to be rigorous. But a typical occupancy function might be, let me think now for a second. Just let me think for a second. Rho of E. Okay, if you're talking about electrons in metals, and you're talking about electrons that are not under the subject or not under the influence of a potential, you might have, let me think now, I'm just trying to think. Okay, you might have the following occupancy, or the following density. So 3n times root E over twice E Fermi to the 3 over 2. Just accept that. I'm saying that this is the number density in terms of energy. Or sorry, yeah, the density of states in terms of energy. Then what's the occupancy? I'm going to tell you, if we're talking about electrons, we're going to use the fermi-dirac statistics. E to the E minus mu over kT plus 1. So how do I find out the total energy in my system corresponding to all my electrons? How much energy are my electrons adding to my system? I'm going to say it's the following. E is equal to the integral from negative to positive infinity of n of E times E dE. That's going to be equal to the integral from negative to positive infinity of rho of E times F of E times E dE. And finally, let's put that all together to give your final integral that you have to calculate or evaluate in order to get your total energy. It's going to be 3 times the number of particles times the energy per particle divided by twice the Fermi energy to the power of 3 over 2 multiplied by the occupancy function of e to the E minus, now for a reason I'm not going to explain, you can actually make this to be the Fermi level, over kT plus 1 times E dE. And that is the typical calculation to get the total energy in your system. And finally, how would you get the total number of particles in the system? Well, this would be n, you'd get rid of E, so this would be over 1, and you'd have to use a different occupancy or a different density of states formula, one which of course didn't have n in it. Alright, so look, I hope that gave you an insight into the density of states, the occupancy, the number density and the number. Thanks for watching. Please pass it on to your friends and subscribe to my channel.